Okay, so in this video, I'm going to explain what might look like fairly complex or confusing notation. This notation is actually called, it's a shorthand notation, and it's sometimes referred to as line notation. Basically what it is a much simplified representation of electrochemical cell. We can also look at it as an actual redox reaction, and we'll see how we get the redox reaction out of this notation. So let me get started. So first of all, line notation or shorthand requires some specificity. First of all, the anode and the cathode are basically shown, and this includes states at the anode, the cathode. Contents of the compartments, that is the half cells, is also shown, and any boundaries between phases is indicated. Shorthand is organized in a specific fashion, and so in this case, anode to cathode, specified. And then at the anode, we start with the species that is oxidized and then show its product. And at the cathode, we then show the species that is reduced and the product of that reduction. So if we look at the shorthand again, as it says, we proceed from anode to cathode. So here is the anode. So at my anode, I have iron solid being oxidized. So this is my reducing agent. It gets oxidized, and there's the product, Fe2 plus, of the oxidation. And here's some specificity as well. It's iron solid, so I have an iron electrode. It's solid, and here is my other component of the compartment, and that would be Fe2 plus aqueous. And it states the concentration, so this is a standard concentration, 1 mole per liter. On the other side then, we have our cathode, so there's the cathode. And again, we start with the species that is being reduced. And so this is copper 2. And so copper 2 is my oxidizing agent. So copper 2 gets reduced. And when it gets reduced, it forms copper solid. And so the again, the contents of the compartment, there is my aqueous solution of copper 2, and I also then have my solid copper electrode. I didn't show solid here, but I have my solid copper electrode, so that's the other component of that compartment. Now in terms of showing phases, this is indicated by these lines here. So this single line in the anode and this single line in the cathode, those are phase boundaries, so they're known as phase boundaries. And a phase boundary then is simply that single line demonstrating or indicating that we go from, in this case in our anode, a solid state to an aqueous state for our species, our iron, and in the cathode we go from the aqueous state separated by a phase boundary to the solid state for our copper. So phase boundaries are these single lines. And the last thing we have to show is this double line, and so that double line, you may have guessed, is our salt bridge. So that's the separation between the two half cells. So there's the sort of specificity you're looking for. Anode to cathode, reducing agent to its product, oxidizing agent to its product. We show phase boundaries separating components of our half cells, and we have a salt bridge showing separation between the half cells. Now the other thing we can get from this line notation, because we now know some specificities, we can get the different types of reactions that take place in here, the half reactions. And so there's one half reaction. So this is the half reaction at the anode, iron, so iron solid yielding iron 2 plus electrons. And we also can get the half reaction at the cathode, copper 2 plus 2 electrons yielding copper solid. So that is an oxidation, that is a reduction. Well, if we know that, we can very easily write the overall equation. So the overall equation for this particular electrochemical cell is iron solid plus copper 2 plus ions yields iron 2 plus copper solid. So again, the line notation very quickly allows you to generate the overall redox equation. So that's what I was saying earlier. You can see the redox equation in the line notation, and there it is. The last thing we can get from this without too much difficulty is our electrochemical cell potential. So remember, we can do that by adding the oxidation potential and the reduction potential we get from our table. So let's go to our table. And so here we're looking for copper 2. So there's my copper 2. So there's the cell potential for the cathode, 0.34 volts positive. And here's iron 2. So there's the cell potential for my anode, negative 0.44. Now remember, that's my anode written as a reduction potential. So because I rewrote my reduction potential as an oxidation potential, I would reverse the value of the cell potential. And so there, now I can add my cell potentials and get my overall standard cell potential. So there's the standard cell potential, 0.78 volts. So as you've seen, it's pretty easy, pretty quickly we can generate an overall cell equation and a cell potential from line notation. So let's look at one more example. So consider interaction between fluorine gas and iron 2. What would be the line notation, the overall equation, and the cell potential? Well, we need to go look at our our cell potential table and look for the two reactions. So here's one. There's my fluorine, F2 plus 2 electrons yields 2F minus, positive 2.87 volts as a cell potential. It's definitely going to be our cathode. It's the highest on the table. And we're looking for iron 2, which we just looked at. That's down here. And so again, a lot lower, so it's going to be our anode. So we can go back now, start filling that in. And so there is my half reaction at the cathode. There's my half reaction at the anode. So they're still written as reductions. So again, what would be the line notation? We can write the line notation now, but maybe it's a bit easier to write the overall equation first. So let's do the overall equation by reversing what has to be reversed. So this is our anode, so that needs to be reversed. So if we reverse that, it becomes Fe solid yields Fe2 plus 2 electrons. And so we would change the cell potential for that to an oxidation potential, so positive 0.44 volts. So we're done with it. So now we can actually get the overall equation. So we just add these two, and notice the electron transfer is already equal, so we don't have to multiply anything. So here's our overall equation. Fe2 gas plus iron solid yields 2F minus plus Fe2 plus, and that's aqueous. So there's the overall equation, and that should be balanced. 2 times F, 2 times F, 1 Fe, 1 Fe, charge. 2 times F, 2 times 1 minus, 2 plus, that's balanced by charge. So there's the overall equation. Well, very quickly, we might as well add those cell potentials as well, and we get our cell potential. So 2.87 plus 0.44, so that's going to be 11, 9, 13, and 3.31 volts, if my math serves me. And so that's positive 3.31 volts. Remember, positive cell potential has to be positive. Okay, so there's overall equation, cell potential. Now we can look at our line notation, and we can use the overall equation for our line notation because it shows us, basically, kind of shows us what's happening. At least it indicates our species that react. So here we have our oxidizing agent, F2, and our reducing agent, iron solid. So here we're going to start with our anode, and so that is Fe solid. And then we have a phase boundary because it's iron solid. We can use an iron electrode as our electrode in our anode, and then its product, it's converted to Fe2 plus, and that's aqueous, and under standard conditions that would be 1 mole per liter. Then we have our salt bridge. Then we have what is our oxidizing agent, which is F2, and so this is F2 gas. Okay, now there's a phase boundary because that gets converted to 2F minus, and that is also aqueous, and that would be 1 mole per liter. But that's not a solid electrode. So here we need an inert electrode. So we need another phase boundary. That's aqueous. There's another phase boundary, and so we could say use a platinum electrode, PT for platinum. So that would be the line notation for this electrochemical cell. There's our reducing agent, Fe solid. It gets oxidized to Fe2+. There's our oxidizing agent, F2. It gets reduced to F-. But we need this inert electrode because we're dealing with a system that does not include a solid electrode. And so that's, in a nutshell, how you come up with line notation and the uses of line notation. So it is a very handy shorthand. And that concludes this video.